Example problem 6.3 is part of class number 16. It's a relatively long problem. It's the same one out of the book. I'm going to walk through it. Hopefully this will help you out in a more complicated problem. It wouldn't hurt to use a straight edge. I'll approximate like the angles on this here. So like approximate like that. Approximate like that. Something like here. There you go. And we get a lot of forces on there, so maybe I'll actually draw this thing out here. Let's see, it's broken into thirds kind of here, and I guess like that. Did a very good job of that. Neck hurts. Okay. And something like that. It doesn't look very pretty. And reaction forces right here are of RAY, and I'm just going to put the RAX there, but I could just tell by inspection that's going to be 0. There's nothing in the X direction, right? Let's see, we'll put this 1 kilonewton. It's kind of annoying. It's got all these on there. 1 kilonewton, 1 kilonewton, 1 kilonewton, and 1 kilonewton. We'll see soon this is sort of like the way you do a distributed load, is that you could put individual things. You could think of this as like being snow or something that's like distributed across the entire top. So we're just putting them at individual places. As a concept that like they covered like chapter 7 actually. RLY. And if we take a look at the distances here, they're by 5 meters, right? So there's 30 meters across here. So if you're going to do the sum of the moments, which one's the easiest one? I decided to take it about L. So, and there's a whole lot of them. So I decided to come over to the side over here. Didn't want to be lazy. Go RAY. It's going to be times 30, right? So because we're taking it about L right here. And these are all, and that should be a negative right there, right? Yeah, negative. And then because that would be clockwise. So the rest of these are counterclockwise. So I could go. I forgot these forces too, right here. So they're hanging something from the rafters that's kind of distributed by 5 kilonewtons in each of these. So I forgot to put those on there. So like 1 times 25 plus 1 times 20 plus 1 times 15 plus 1 times 10 plus 1 times 5, right? Because it just comes down in increments of 5 as you're going across. And then these are all clockwise right here, so it's negative 5 times, and it's going to be 25. And then negative 5 times 20, and then negative 5 times 15 equals 0. And if you do all of that out, my calculator said that's 12.50 kilonewtons upwards. And we might want to find out what RLY is, and then we just do the sum of the forces in the y direction equal to 0. And boom, kaboom, kaboom, kaboom. We say that it's going to be 12.5 upwards, and then 1, 2, 3, 4, 5. So we go negative 5 times 1, I could do that. And then 1, 2, 3, 3 times 5 down, and then of course we have plus RLY. And we can find at RLY the reaction. Riley, that's a good one, right? Riley is 7.5 kilonewtons upwards. Now our goal, which we probably should have read in the beginning, is to get FH, so that's going to be right here, and to get GH, and then to get GI. So there's a bunch of different things we're going to use, but we're trying to use method of sections, MOS, right? Method of sections. And so I'm going to follow along the way the book did it. We could use a little different, clever little tricks and that kind of thing. That's one of the difficulties in learning to do this particular type of assessment or problem. Is there like a bunch of different tricks that you could try to employ? But here we're kind of using more of a straight ahead type of thing, and coinciding with what's in the textbook. So I keep looking over here. I'll put it over there. Something stuck on my teeth. It's kind of gross, huh? A little more centered. Not literally. Figuratively. Not figuratively. Literally. Yeah. Let's see. So I'll draw this section right here. And my strategy here is that I'm going to try to find, first, FGI. So I'm going to try to find this guy first, the one that's in between here. And I'm going to do it by taking the sum of the moments about H, right? And the idea there is that we want to get rid of as many as unknowns as we can. So I'm going to take my section, like right along there, and what we're going to do here is we're going to assume all of them are in tension. That's my approach to the thing, and I will try to be consistent in that, to try to take everything in tension. So what we'd find here is that we would take, and that would be FH right there, right? Because it's going between. Let me zoom out a little bit. Physically zoom. It's the physical zoom. There you go. So we see more of the paper. All right. We also have this downward one here, 1 kilonewton. And let's see, this FFH. And then we also have right here, and that's going to be FHG, right? Yep. No, wait. I think I miscalled one of these on mine. Let me make sure I fix that. AFGH, right? Yeah, I'll let you go in alphabetical order. So GH, right? FGH. And then we also have another guy right here, right? Is another 1 kilonewton. Don't want to forget him. And I guess I could draw that guy in there. And then we also have this reaction right here. We know that reaction, so I'm going to label the number instead of keeping it as a variable. And so what we're going to do is we're going to take the summation of moments about H is equal to 0. Like I said, this is a long problem, by the way, so I don't expect it to be very long. And we do, one of the things we're going to need is we're going to need this height right here. And in order to get that height, we're going to need, well, actually, what we could do, we know that this is 8 meters tall, and we know that this is like 1, 2, 3, right? So it's actually divided into thirds, and by equal triangles, you could say that that's 8 times 2/3, and that comes out to 5.333 meters. Trust me. All right, so taking the summation of forces about H, we'll say that 7.5 is going counterclockwise, and that's going to be to this position, which is 10, right? Yep. We also have this 1 kilonewton that's going, did I say that right? No, it's going clockwise, right? Because we're taking about H, so it's going clockwise. So it's 1, and it's going to be times 5. Okay. And then we have this guy, who's also, this FGI, is also going clockwise. So it's negative FGI, and then that distance is 5.333 equals 0. So FGI is 13.13, and it was a positive number. We assumed it was in tension right there, right? So therefore, that's going to be a T. Now we can mess around, I think, and try to get some of these unknowns. All right. So what in this diagram right here, when we've just found this, we don't know this FGH and we don't know this FFH. So let's go ahead and redraw the thing. And like I said, there might be some like monkey business we could do to mess around with that. Using the sum of the forces, we could try and some of the schemes that we might try is changing the axes and that kind of thing. But let's just march through this here. Now we're going to draw it. We're going to extend it, and instead we're going to try to take the sum of the moments about G right here. So we need to incorporate G. We could actually probably have used the same diagram, but it probably would have, chances are, confused us. It's good. It's easy to get confused, right? So we're going to draw this, and I'm going to draw dot, 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 and then dot, 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 just for the time being. I might make those darker here in a second. And so make that same breakdown right here. Here's that little Irish jig. That's Professor Haddad's ringtone. Hear that a lot. My FBD kind of is going to get in the way of stuff I want to include, so I'm going to put it back up here. All right, let's see. And all right, so here's going to be the trick. I'll put all these other things in here, and then I'll tell you what the trick is. It's a little bit of a cheat, I think, and you're going to have to think about this carefully as we're putting it in here. It's 1 kilonewton. Okay, so first off, we're going to do it about G, but we've cut it somewhere kind of in this region right here. But some of the cheat is that we're going to like cut it like really close, like right in there, okay, and then cut the rest in there. So we showed it in the middle here, but we're going to cut it like right along there, like right where the pin is. We're almost going to take the pin out. Think we're just taking the pin out onto the thing. And so the force would be coming up this direction. And maybe we could kind of ghost it in there. And so then it would have components there and there, right? So we could think of it as just cutting it just before it gets right there, so we see the internal force that's coming up in there, right? And we're saying it's just in there for a second. And now this force right here is convenient for where we taking it at G, because it's going to run through there. And this force, which we just found, but we don't need it for this, is going to be right there. Did I forget anybody else? No. All right. Well, hopefully you kind of see some of the idea. So one thing here, let's define this angle, alpha, right here, and that was going to be like rise over run. That would be 8/15. Is that what I did? Yep, 8/15. So that's the inverse tangent of 8/15. And what we end up with is a 28.07 degrees. And okay, so what this is going to be up here, this is going to be the FFH, but it's going to be times the sine of 28.07 degrees. And then this guy right here is going to be FH times the cosine of 28.7 degrees. So what you end up with, if you take the sum of the moments about G right here, we've effectively gotten rid of this guy that we don't know. We got rid of this guy too. And by the way, one of the things that I'm saying here, you could potentially, if you wanted to, put that 1 kilonewton down, right down in this way, right down in there. Or you could say that we're just before he gets there. I don't know. I think maybe might be proper to put the 1 kilonewton in there. Right there, right? Onto the thing. In any case, it passes through G. Also, the vertical component, that sine, that also passes through G. So we don't have to use the thing. Taking G was our strategy to get rid of all of that. So I'm going to say that this guy is going counterclockwise, so FFH times the cosine of 28.07, and its perpendicular distance is 8. Don't need this guy, do need this guy, so -1 times, his moment number is 5, and then this guy right here is a -1, and his moment number is 10, and then this guy is going counterclockwise, right, about G, so he's a positive 7.5, and his distance should be 15. Is that right? Yep, 15, and it all equals 0. If we find the FFH right there, we get a negative 13.181 kilonewtons. That means that it's actually 13.81 kilonewtons in compression, right? So we drew it wrong. It was easier to draw it as tension though, and then just if you get negative, find out that you did it. Okay. And then the last one is FBD, right? So that we found the FFH, which was part of what we were setting out to do. Found the GI. Now we need to get GH, and their strategy for that is now to redraw this. And once again, if you were really desperate to save on paper, you probably could have. You probably could have reused stuff, but it's just going to cause problems for you. What we're going to do here, I'll draw it to right to there. Okay, and okay. So here is one, and I'm going to do another example later on. And I'll record this one from another book that I thought was quite clever. Not showing this right. I accidentally left it out of there. This is down. This is down. Let's see, this goes out that way. All right. So let me put these on here. 1 kilonewton. 1 kilonewton. There's a clever trick when you have a different configuration that you might want to include in our arsenal of tricks. See, we can go through this guy right here. So our trick this time is going to take the sum of the moments about this point L, right there. So, and I think we just found out, didn't we just find out that FFH was the other direction? So why did we draw it that way? I don't know. We just found that it was going to be in compression. So I should have drawn it that way. And I'll leave it as FFH. I don't care how to name this thing. And I didn't label these guys either up here. FGI, like the GI track, or GI Joe. FGH, it's something we're trying to get this time. And, okay, so we've cut this thing. Okay, so here is that FGI. Now, but we've separated this thing out like right here. So what we can do is we'll assume this guy is in tension, right? I don't want to draw him in there. So I'll draw in the thing, but it doesn't actually reach the bottom right there. Is what we want to try to do is have it's in tension. We assume it's in tension here, so it has an X component to it, and it has a Y component to it, right? So this is going to be FGH, and it's going to be the cosine of the angle that's in there. But if you take a look at this right here, boom, boom, boom. Okay, no, I got to get that beta. Let's see, how did I define? I defined this beta this way right here. So I said that beta, that angle that we have right here, that's why I did cosine, is because it wants to be, yeah, so that angle is going to be the same as this angle right there, right? So that's why it's cosine, not that one right there. And that beta, its opposite length is 5, and its vertical length is that same 5.33. So let me see here. I'll tell you my other computer that I'm still here. So I'll take the inverse tangent of rise over run. And so the rise in this case is opposite over adjacent, I should say. So this opposite is going to be 5 over 5.333. Did I do that right? I don't know where I did that. I did it somewhere. Oh, there it is down at the bottom. Okay. And that gives me a 43.15 degrees. So this is my, I'll just call it beta there. Okay, I'll leave it there. And then FGH sine of beta. Right in there. Okay. I think I'm okay for all these other things. So I take the sum of the moments about L right here. And what we notice is that this guy passes through L, this passes through L, and this passes through L. So what we're really doing is we're trying to isolate so that the things that we don't know there's only one of the things that we don't know. In this case, it's this component right here. And that's going to be, one second, I have someone knocking at my door. So I have to stop. Okay, so I had a knock at the door, but we're back. What was I doing? Okay, FGH times the cosine of 43.15. You don't need to see my hand in there. And that distance is going to be 15. Is that true? Yeah. And it should be counterclockwise, so we're doing it about L. Other things, let's see, did I put in, I think I should have put in that guy right there, yep, 1 kilonewton. And he's also, is he also, yeah, he is, okay. He's also counterclockwise, so we can kind of see it. We're going to get wrong. It's going to be compression instead of tension. But that's going to be times 10, because there's 5 and 5, and then plus a 1 and 15. And I think I got them all, right? Because it's about here, so we don't have to worry about here, don't have to worry about that, don't have to worry about that, don't have to worry about that. So that's our strategy right there. So we get an FGH is going to be equal to a negative 1.371 kilonewtons. Therefore, it's equal to 1.371 kilonewtons compression. So you get the idea of the method of sections. It's a little intimidating, but you need some practice with them. And if you work through these, you'll just get better and better at them, and they'll seem like they just make perfect sense. So that should be our video conclusion for this sample problem. And I'm glad I don't have to do this in class, because I think it would take a lot longer to do. Ta-da!